Hi everybody. This series is going to be about our electromagnetic fields and waves. I actually, used this book as the reference one, Fields and Waves in Communication Electronics by Ramo and Winnie van Duzer. That's I used the textbook as my PhD student at actually not RIT, but at the State University of New York at Binghamton, New York. So that time we are required to submit homeworks after each lecture, 5 to 6 problems through the end of the semester. So I have idea how to get my homework solution and relate that and put on my YouTube video. So it's a good opportunity for students to recall or refresh something about electromagnetics, which is very important in electronics as well. I pick up problems at the end of each chapter. So we're going to have more problems starting from chapter 1 through chapter, I don't remember, maybe 10 or 12. And that's going to be more complicated. So I'm going to put in series 1, series 2. And then you probably learn from series 1 and should not have a difficult time to understand, problems later on. Let's do 3 problems at this point for the start. I have let's start question 1. As you were to calculate the ratio of electrostatic force of repulsions between 2 electrons to the gravitational force of attraction. Assuming that Newton's laws of gravitation holds, the electron charge is 1.602 10 to negative 19th Coulomb. Its mass is 9.11 10 to negative 31 kilogram, and the gravitational constant K is 6.67 10 to negative 11 Newton meter square per kilogram square. Well, let's just take a look quick. For electrostatic force, you know that 2 electrons will repulse each other because they have the same negative charge, right? And also you want to compare to a gravitational force. In this case, you know exactly that your gravitational force is going to be much less than electrostatic force because the mass of electron is very small. That is the 9.11 10 to negative 13 kilogram. So what you need to do is just find the ratio of your electrostatic force and your gravitational force. Okay, let's get started from electrostatic force between 2 electrons. You know that for Coulomb force, F equal to Q1, Q2 divided by 4 pi epsilon r squared, where E or Q is the electron charge that's given constants, and your epsilon is the permittivity of the media. In this case, let's assume that electrons are in free space. So your epsilon is going to be epsilon 0. Basically, your epsilon or permittivity equal to epsilon r multiplied by epsilon 0, where epsilon r is relative permittivity, and your epsilon 0 is the permittivity of the free space in the unit of farad per meter. The same as when you talk about the unit of capacitance, that becomes farad, right? So that's related to each other. And r is simply distance between 2 electrons. Now for gravitational force, you know that F equal to K, that's the gravitational constant multiplied by M1, M2. Just like you calculate for the gravitational force between the Earth and the Moon. But in this case we have 2 electrons, so that's become the mass of electron squared divided by r squared, which is the distance between 2 electrons. Same as the way you calculate for electrostatic force. So you simply divided equation 1 by equation 2. You end up with E squared divided by 4 pi epsilon k m e squared. You simply plug in constant for epsilon 0, for k, for me, for e. And for epsilon 0, that's the 8.85 10 to negative 12 farad per meter. So you enter between, the ratio of electrostatic force and the gravitational force is about 4.167 10 to 42. That's far high. This means the gravitational force is much less than the electrostatic force. Okay, so that's we start with electrostatic force and the gravitational force. Problem 1.2f. They ask you to calculate the electric field at points along the axis perpendicular to the center of a disk of radius A, located in free space. The charge on the disk is a surface charge, or lowest Coulomb per meter square, uniform on the disk. Okay, as you do, calculate for electric field. So at this point, let's put this point as P. What total electric field going to be at this point? Starting from drawing the diagram. So you have a disk right here, and you have looking for electric field at P, where is the phi is at the distance z from the center of the disk. So you apply to be easier, you know that your dE, you can start from here, dE equal to dQ divided by 4 pi epsilon 0 r squared. This is in free space. And then if you look at the picture here, at this element of the disk, when you have a uniform charge, low S, so your dE is going to point out in this direction, and you can consider only x-axis and y-axis. Look at two of these in y component. This is also your E, right? Because this one seems to be like symmetry. You separate between the top and the bottom part of your disk. And this one also creates your dE, and you have a dEy component, and you have also dEx component. But look at this. For the dEy component, that will cancel out, correct? Because it's pointing out on the opposite direction. So you end up with only dEx. So actually I put this one as the dEx, or E total going to be if you put simply dE, if I put D here, you can show integration sign out, you're going to have dE equal to dE cosine theta, which is the this component. And to add them up, you just do integration. Okay, dE equal to dQ divided by 4 pi epsilon 0 r squared, and your dEx going to be your dE cosine theta, and for E you do have integration, so you just plug in your dE in this equation. What you need to work out is you have to write R in the term of cosine theta, or in the term of R, in the term of phi. You can see the small segment on the disk. Now, what is your dQ? Since the lowest or the surface charge density is given, you can calculate for your dQ from the small section of your disk. That's going to be rho s multiplied by ds, or the small area. What is the area? Area is the width multiplied by the length. When you have the length to be d phi, right? The length is going to be r multiplied by d phi. So this is your length, and multiplied by the thickness. So simply that's become dr. So you end up with this is your ds, and you multiply by rho s. The surface charge density does give you what? dQ, right? Still divided by 4 pi epsilon 0 r squared. Does give you a dE. Okay, you simply just plug in this term in this equation. Now you take a look at cosine theta. This is your theta, so your cosine theta is going to be z divided by the capital R, or r squared plus z squared plus r squared to the power of 1 over 2. Okay, and this is your r, this is your z. So that's why you have this term. You plug in right here. Just be careful when you work out. And your cosine theta simply I put as that z divided by z squared plus r squared 1 over 2 here. So you rearrange the term, you're going to end up with 2 pi cancel out 4 pi, so you have 2 left, and z become constant because you integrate with respect dr, and this one you integrate d phi, you form dv from 0 to 2 pi, right? Because one circle here 2 pi, so you end up with 2 pi. Now consider integration over rdr over z squared plus r squared to the power 3 over 2. You let this term z squared become v, and dv by dr does give you 2r, or rdr. This one going to be dv over 2, right? So you can integrate. Okay, you can work out on this one. I don't have to repeat, because the other thing that you need to work on electromagnetic equations. That's will use a lot of math. I mean calculus. So make sure that you still have a good understanding about how to do calculation of in the term of integration or differential. So from the calculation, I end up with the integration of r dr divided by z squared plus r squared to the power 3 over 2 to be 1 over z minus 1 over z squared plus a squared to the power 1.5, and the limit of integration is from 0 to a. Then this is your e. Whatever you have, you calculate. You need to multiply back with lowest z divided by 2 epsilon 0. So you end up with this term for electric field at P point in the figure above. Now for limit of a go to infinity, you can see that this term very large and this term drop, right? So you end up with 1 over z in the bracket. Z and z cancel out. You end up with e to be rho s divided by 2 epsilon 0 when your a is very large, or your disk has a very large diameter, radius or diameter, doesn't matter. Okay, so what we get from this problem? Well, this problem reminded you how to apply Coulomb's law, dE equal to dq divided by 4 pi epsilon 0 r squared. And then you know how to do calculation. Actually, you know how to do a calculus in the term of integration. And one point is that the electric field along the axis of your disk, that's you have only your perpendicular component to the disk. This means from the picture you have only EX component. You don't have an EY component, because EY components are cancelled out. Okay, that's the conclusion from the problem. Next, let's do one more problem. Actually, to calculate electric flux emanating from a point charge Q and passing through a mathematic plane disk of radius A, located a distance d from the charge. The charge lies on the axis of the disk. Show that in the limit where A over d go to infinity, the flux through the disk becomes Q over 2. So you have a point charge Q here, and you also have a disk from the distance d from the point charge. This one asks you to calculate for electric flux. And the disk has the radius A. Okay, you need to set up the equation for electric flux. Electric flux, that's going to be let's put a small portion of electric flux that the sign going to be d dot ds. This is from Gauss' law, right? Here. And what is your d? D is equal to Q over D, or how do you know D? D simply become Q. D actually equal to epsilon E, right? And this is from a Coulomb Force. Oops, sorry, Coulomb's law. That's the equal to Q over 4 pi r squared. You know about that. And r actually is become a unit vector of your d, the electric flux. And you still dot ds. Or the whole thing just right here is actually your d, electric flux density, right? And when you dot, you have the same thing. You have only the E component that parallel along the axis of the disk. From the picture, you have only your Y component, right? Your E, as we worked out on the problem before, the previous problem. So that's why I put like ds perpendicular. And as you know, the area of the sphere or whatever divided by r squared, that's give you the solid anchor. So that's why I put ds over r squared as the omega. That's a solid anchor. And from the definition, when you dot two vectors, that's become the magnitude of the r multiplied by the magnitude of your ds, and then cosine theta. So that's why you have cosine theta right here. R, the magnitude of the r vector, unit vector, of course, is 1. What about your ds? Look at your ds. From the small sector here, okay, your ds is actually the length multiplied by the width, where the width is the low, where rho is the radius, arbitrary radius, and the length become rho d phi. Okay, so you have d omega here. Now you can continue working on the equation. What do you have? This is your the psi, and you can calculate for psi simply by integrate the whole thing. This is your omega right here, and this is your omega when you work out in the term of r, in the term of rho, phi, and theta. So you have q over 4 pi, and you multiply, by the integration of this term, the whole term. And you take a look at theta. What is your cosine theta? From the picture, this is your theta. So your cosine theta simply become what? Rho. Oh, sorry. Your theta right here. So your theta actually is going to be what? What did I do wrong here? Sorry about that. I should draw the triangle right this. This is your theta. So actually become d divided by r. You put the capital R, okay? And your r simply become square root of d square plus rho square. So that's why I have a cosine theta equal to d over d square plus rho square. power 1.5. And also you have r squared here, so that's become r to the power of 3. And you put r in the term of d and rho, become rho squared plus d squared. Your job is to do integration. Okay, this is how I work. I pick up this term, since the rho squared plus d squared, when you differentiate with respect to the rho, you end up with 2 rho below. D is constant. Or your rho d rho, that's going to be d rho squared plus d squared divided by 2. And just do simply integration. You know that this is the basic calculation of integration. That's why I put a note here. Integration of v to the power n dv is equal to v to the power n plus 1 divided by n plus 1. And this is my final electric flux. Now you take limit a over d go to infinity. This term drop because the denominator is very large, right? A go to infinity, so you end up with your electric flux actually become q over 2. So electric flux, you can see at this point, it doesn't depend on the distance between the disk or d in this case from the point charge. Is depend on only on what? Q, and divided by 2. You're probably surprised about that. It's become a constant. Yeah. So we will move on to do more problems. Still working on Gauss' law and electric force. But later on we will move to plane wave. We will move to dielectric. You know, it's going to be more complicated. So this one is just for the start, for you to refresh. Okay, so that's all about the video this for this series. Okay, bye.